All right, we are back to continue the example that won't end, as if 42 minutes wasn't enough. We still haven't finished this problem. We haven't talked about the thermal efficiency yet, so we need to do that. Now, what we're going to do is we need to look at our Q's and our W's. So we need to find Q and W for the entire cycle. So let's just make this little table. It'll be easier that way. So those were the processes, and then let's go through and write down the Q values and then the work values for each of the processes. For 1, 2, we had Q of 1072.24, work was 123.79. For that second process, we had a Q of 0, work was 544.25. For the next one, we have negative 625.47. And work was negative 37.13. Finally, we had a Q of 0, and then a work of negative 184.16. Now what we're going to do is we're going to sum these up. So the sum of this first column is 446.77, and for work, we got 446.75. All right, and they should be equal. I'm not sure why. It's probably my rounding, but remember the work coming, the Q and the W have to be equal for energy balance. So this is probably due to my rounding, but we'll say it's close enough for now. Now for efficiency, we got two ways we could do this. The first one, remember we have our eta equation. So for this one, we will have the equation for the work of the cycle, and then we are going to put that over QH. Now remember QH, remember what that is. That, if we look back at our notes that we did, here, let's look at this picture. QH is going to be for this process right here, because this is where we were dealing with that hot reservoir. This was at our high temperature. So we need the Q for this process right here. So this is process 1, 2. And work of the cycle, that's the total work that you had. So that's going to be this value here. All right, so we just take this value and then we will divide it by QH, which was 1072.24. And the units for both of these were the same, so I'm not going to write them out, but they were the same, so that works out. Now let's go ahead, and when you divide that, you're going to get 0.4167. So that means your efficiency is 41.67%. That was one way you could go about finding the efficiency. The other way is to use the max equation. And can you think about why we can do that? We can do that because the Carnot cycle is a reversible cycle, right? So that means, remember, reversible is like ideal. So the max efficiency would be found using reversible processes. So here we can use this equation. And this equation, if you look back in your notes, is 1 minus Tc over Th. And we know what those are. We had 500 and 100, right? So that was in Fahrenheit. So if you put it in Rankine, we're going to have 1 minus 560 degrees Rankine over 960 degrees Rankine. And conveniently, you're going to get the same number. All right, so 41.67%. Now, basically what this is telling you, we didn't even have to go through and calculate all of these values. We could have just looked at the temperatures of the reservoirs and already known the efficiency here. All right, so, but that's how you would look at efficiency. You got to look at the total for the whole cycle when you're doing this work calculation. All right, and QH, remember that's the heat transferred from that hot reservoir. Okay, so that is the end of that example. I know this video is way shorter than the last one, but I didn't want to stop in the middle of part of the equation development there in that last video. So hopefully that helps you out in understanding the Carnot cycle. But a lot of things are going on in this cycle. Key takeaways here are that we have the 2 isothermal processes, and then we've got the 2 adiabatic processes, and they're going to be reversible. So reversible means this is going to be an efficient cycle, theoretically. And we saw it was almost 42%. But nonetheless, theoretically, this should be a good cycle. So that's basically what it looks like. Hopefully that gave you a good review of some of the concepts we've already covered before this section. And I will see you guys next time.